Hello folks, this is my second lecture about bonding, chapters 8 and 9 in both the Brown and Zumdahl textbooks, and we're going to start by discussing polar molecules. What we learned in the last lecture was a discussion of polar versus nonpolar covalent bonds, and with polar bonds what you've got is a difference in electronegativity between the atoms that are involved. So unless you've got something like chlorine gas, where chlorine is bonded to chlorine, and so they're exactly the same strength of electronegativity, most of your covalent bonds are going to be at least slightly polar because they'll be slightly different. So we've got polar bonds versus nonpolar bonds. So if you look down here, you've got oxygen gas here, oxygen sharing with oxygen. They're going to be perfectly matched in terms of their electronegativity, so it's going to be a nonpolar bond. But if you've got carbon bonded to oxygen like we do here, oxygen has got a much higher electronegativity than carbon does, and so the electrons in this double bond will be spending more time over near the oxygen, which gives the oxygen a slightly negative charge compared to the carbon. Whereas this bond as well with the oxygen versus the hydrogen exhibits the same thing, where oxygen has pretty strong electronegativity, and so it sucks a lot of the electron presence over towards itself in this bond. So hydrogen is doesn't have much time spent near electrons. Ooh. So ends up having a slightly positive charge, and oxygen has a slightly negative charge. And the funny little symbol that they'll draw to indicate that is this little dude here. Boop, boop, boop. That is I think that's a lowercase delta, and that will be drawn on the molecule sometimes with a little plus or a minus to indicate that it's the polarity of it. Kind of weird. Anyway, so that's polar bonds. Now polar molecules are slightly different because you have to deal with whether or not the molecule is symmetrical. So let's look again at our oxygen molecule here. Because because these are the same dudes, like, yes, it's going to be, what you're going to end up with is a perfectly symmetrical system here. So the electrons that are being shared perfectly well, because they're the same electronegativity, you end up with exactly the same amount of charge on the left versus the right end of this molecule. So this ends up being a nonpolar bond with a nonpolar molecule in O2. In contrast, you've got polar bonds here in carbon dioxide, as I mentioned before, because the oxygen is a stronger electronegativity than the carbon. So the oxygen is pulling the electrons over to the left. So it's slightly negative on this oxygen, and slightly positive on the carbon, and slightly negative on the oxygen. And again, my computer is eating my marks. I don't know why. But the thing about that is you have a slight negative charge on the left and a slight negative charge on the right. So which side is slightly negative? Well, compared to each other, neither one. So what you end up with is a molecule that is actually a nonpolar molecule, but that contains polar bonds. You have to understand the shape of the molecule in order to be able to predict whether it's polar or nonpolar molecule, and you have to understand electronegativity in order to predict whether the bond is polar. So yeah, you end up with, what do I have? Symmetrical negatives here. Water, in contrast, is a bent molecule, which you don't know that yet because we haven't learned about Vesper theory this year, but we did it last year, so you do know it. Anyway, water is a bent molecule. You've got 4 electron domains. You've got this guy, the 2 lone pairs, and this guy, the bonds. And so they're arranged in a tetrahedral shape around the oxygen. And so you end up with the hydrogens being at an angle to each other. This actually, since it's water, it's 104.5 degrees, by the way, because these guys push harder. But I'll get to that later. So they're at an angle, and what you end up with is a whole bunch of negative charge up here. You've got 2 lone pairs of electrons, and it's hogging the electrons from these bonds. So the oxygen is very negative E compared to the hydrogen end. So it's negative up here, and it's positive down here. So what you have is these bonds are polar, and because this is a non-symmetrical molecule, you have a negative side and a positive side. So you have a polar molecule, and often the language used to describe this is that it has a dipole moment. Dipole meaning it has two poles, like, you know, the North and the South Pole. And moment, like it has momentum, like if it was in some sort of electrical field or something, it would go nee, 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 and move across. So it would have momentum. So it has a dipole moment. That's what they say. Okay. So the thing about predicting whether or not the molecule is polar is that you have got to be able to draw your Lewis structures and use your VSEPR to predict the shape, because you don't know if it's symmetrical unless you know what shape it's in. So let's go and do that. All right. The localized electron model is basically kind of the whole of the description of what the electrons do in molecules when you're using Lewis dot structures and VSEPR for 3D shape and hybrid orbitals to describe exactly what the orbitals are doing with the electrons. That's this whole model. All these three things together combined are describing the electrons that are kind of locally present around each of the atoms and what they're doing in the bonds and stuff. There's another entire model which is called the molecular orbital model, which talks about how the electrons actually are kind of smeared out around the whole molecule, but we don't have to learn that one. So the localized electron model is the one that we're doing, which involves Lewis dot structures, VSEPR, and hybrid orbitals. Bam. Okay. Lewis dot structures look like this. Here we have carbon with 3 chlorines and hydrogen, so that's CHCl3, goodbye H. And it's important to remember, especially step 1, you have to add up all of your valence electrons, and then when you're done, make sure that you've accounted for all of them, because it's really easy to forget and leave 2 of them off, and then it's wrong, because you just made electrons disappear. Way to violate the law of conservation of mass. So your valence for carbon, you've got 4 valence electrons. Hydrogen, you've got 1 valence electron, and chlorine, you've got 3 times 7. So 21 plus 1 is 22 plus 4 is 26. So we need to account for 26 valence electrons. They all need to be present in my Lewis dot structure picture, and if they're not, then I screwed it up. All right, your basic shape, basically all of the questions that you're going to encounter that you get for these Lewis dot structures are going to be giving you a central atom with dudes around him. Dudes being atoms or lone pairs or whatever. You're not going to end up, they're not giving you like really long, complicated molecules because they just basically want you to understand your basic angles and basic shapes. So, and the convention for that is that the center atom is the one that is written first. So the dude in the center, in this case, is carbon. Here he is. Hey, carbon. And the guys after him are on the outside. So in order to get to this, you'd go carbon, and then you'd put a hydrogen and then 3 chlorines. And this thing is totally going to eat all my valence electrons. I know it. Go ahead and draw a single bond between each of them, because there's always at least a single bond. Maybe there will be a double bond. You'll find that out later. So that's your basic shape. And then you fill in your remaining electrons, making an octet for everybody. Except for hydrogen. Hydrogen has got a duet, which is kind of cute, right? So for chlorine, he's got 2 so far that he's able to claim as his own. So 2, 3, 4, 5, 6, 7, 8. And then same for this dude, 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4, 5, 6, 7, 8. So that's how I ended up with this picture for carbon with hydrogen and 3 chlorines here. So, and let's go and make sure that that accounted for all 26 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8 in the bonds. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Good. I have used all my valence electrons that are present. That means I didn't disappear any of them or add any, which means I did it right. So this is the correct structure. One thing that's really helpful is the almost always bond trick. Carbon basically always has 4 bonds. Nitrogen basically always has 3 bonds. Oxygen basically always has 2. And hydrogen really only has 1, ever. Can't have more. There are random weird exceptions, and there's a couple of exceptions that you actually have to know about for nitrogen, and we'll get to those when we get to the problems. But that bond trick is very helpful, because then you can just make sure that you know ahead of time instead of having to really contemplate all the electrons. All right, so that's normal and filling in your octets. There are a couple of exceptions to the octet rule. Not everybody has 8. We knew that for hydrogen, he's got 2. But boron is an exception because of his location. Stop it. Because of his location on the periodic table, boron sometimes can be happy with 6 electrons around him. So you end up with like boron trifluoride and stuff. And that is a molecule that ends up being pretty reactive because it's not super duper happy with having 6, but it can live. So sometimes when you have boron in your center, you can have 6 around him. Beryllium, same deal. Sometimes beryllium can have 4 around him, so you end up with beryllium dichloride or whatever. But boron is the one that comes up more often. So those are the lower than 8. And these are the guys that come up that tend to have more than 8, usually only when they're in the center atom. And what ends up happening is, you know, for example, sulfur will be bonded to 6 different things. Well, if it's got 6 bonds, then you can't have an octet around sulfur. And what's going on is that sulfur with those extra electrons can actually cram them into a 3D orbital, which if you look at the periodic table, hang on, let me go get one. So if you look at the periodic table, you can see that sulfur, the electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p6. But we're in the third, we're in the third shell, and so there's actually some space in the third shell that's the Ds, because 3D is a shell, is a set of orbitals that do exist in the radius that's equal to 3. So basically everybody down here is capable, if they must, of jamming some electrons into that 3D orbital. And same deal with these guys, they can jam it into the 4D, and these guys can jam it into the 5D. So you end up with some molecules with sulfur phosphorus in particular, xenon radon, and iodine, chlorine, and bromine that can have 10 or 12 electrons if they are the center atom. So that's these guys: phosphorus, sulfur, chlorine, bromine. Oh, I didn't mean to have bromine, the essentials. Nope. Phosphorus, sulfur, chlorine, bromine, iodine, and then xenon and radon. These guys here, you end up seeing them as being center atoms that can have more than 8. And we will run into them when we do our problems, which, do I want to do them right now? Let me go see. Yes, I do want to do questions 1, 2, and 3 before we finish the lecture part. So here we go. All right. HCN, this is hydrocyanic acid with the cyanide ion here attached to the hydrogen. And this is going to be, first of all, your step 1. So you've got to add up all your valence electrons. So for hydrogen, let me get my white pen here. For hydrogen, it's got 1. For carbon, it's got 4. And for nitrogen, it's got 5. So we need to make sure that we account for 10 overall valence electrons when we are done, because otherwise we messed it up. So we go hydrogen. Oh, and in this case, actually, hydrogen is not the central atom. Hydrogen can't be. So I didn't mention that as an exception. But obviously hydrogen can't be the central atom, so the next one is carbon. That's going to be your center. So hydrogen bonded to carbon, bonded to nitrogen. You at least have the single bonds, and then you have to account for the rest of them. And if we think about our almost always rule, carbon usually has 4 bonds, and nitrogen usually has 3. So carbon has got 2 right now, and nitrogen has 1. And we've only accounted for 4 electrons. So you kind of go, more bonds, eh? Well, let's do another one here and another one here, and that will give carbon 1, 2, 3, 4, and nitrogen 1, 2, 3. That's awesome. Are we done? Well, let's see if we are done with the total number of electrons, which is 1, 2, 3, 4, 5, 6, 7, 8. We're still missing 2. So you see how it would be easy to say, I'm done, when in fact there are 10 electrons that need to be accounted for. Also, nitrogen currently has got 2, 4, 6 and is not showing an octet. So nitrogen has got a lone pair here. And what's interesting is if you look at this molecule, what kind of bonds do we have and what kind of molecule is it? This guy here, that is a polar bond because carbon has got a stronger electronegativity than hydrogen, and this triple bond here is a polar bond because nitrogen has a stronger electronegativity than carbon. Also, you've got this lone pair here, so you definitely have, how do you draw that funny thing? You definitely have a negative side here and a positive side here. So that's a polar molecule with polar bonds. All right, pH 3. That's 5 valence electrons for phosphorus and 3 total for hydrogen. So we need to make sure we see all 8 of them when we are done here. So phosphorus. With some hydrogens around it. And all the hydrogens are happy, but phosphorus isn't. Because phosphorus is only showing 8 electrons and he really wants an octet. And so what you go is, well, can we do double bonds? No, you can't do double bonds to hydrogen, but you can do a lone pair. So phosphorus has got a lone pair and 3 dudes. All right, this one, oh, we did this one up there. I don't need to do that one again. The ammonium ion. Now this is interesting, and you need to understand this in order to account for your valence electrons. That's 5 and that's 4, but you have a plus charge overall, and so what you end up with is you had 9 but you lost 1, so we've got 8 valence electrons overall. So that's going to be a nitrogen surrounded by 4 hydrogens, and the way that you do this actually, and see, here's an example where nitrogen has got 4 bonds instead of 3, so it's an almost always trick, not an always always trick. Because this is charged, you're supposed to draw it in brackets and put a little plus on the outside so that people know. But nitrogen has an octet, hydrogens have a duet, and we've accounted for all 8 electrons. Bing. H2CO, again the hydrogens can't be in the center, so actually the carbon, the second dude, is in the center. So carbon, oxygen, hydrogen, and hydrogen. Put at least a single bond. Oh, I forgot to count up. That's 2, 4, and 6. So that's going to give us 12 total. This is 2, 4, 6. Carbon wants 4 bonds. 8. Oxygen likes 2, so we're good there. Carbon has his octet, hydrogens have his duet, oxygen only has 2, 4, 6, 8. Bam. And selenium difluoride. Selenium, how many does selenium have? Selenium has 6. Okay, selenium has 6, fluorine has 7 each, so 14, so we need to account for 20 electrons in this. So selenium is in the center, fluorine is on the outside. The nice thing about fluorine, the nice thing about the halogens in general is that if they're not the central atom, if they're an exterior atom, they've always got their 6 dots. I don't think I've ever seen one on the outside that didn't have his 6 dots. So 2, 4, 6, 8, 10, 12, 14, 16, we're almost there. And selenium is pretty sad here. He's only got 2, 4, 6, 8. There we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 20 does. So there's selenium difluoride. All right. So those are all octet rule guys. And then number 2, write Lewis structures for the following which do not obey the octet rule. Oh my. So here we have beryllium, boron trifluoride, and if you remember from upstairs, still not beryllium, boron can be happy with fewer than 8. So let's see if that is the case. And boron has got 1, 2, 3. So that's 3 and 21 is 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. 24, that's it. So here we have a low electron boron trifluoride here. And if you remember from last year, these are the guys that tend to participate in Lewis acid type reactions because they are slightly dying for electrons on this boron here. All right. Sulfur hexafluoride, which is going to be sulfur with 6 fluorines. And I tend to draw this like this. You get a triplet and a triplet, so that your nice hex is arranged beautifully. So you at least have this. Oh, and sulfur has got 6 and fluorine has got 7 times 6. It's 42 plus 6. So we need to account for 48 electrons overall. Goodness. So here we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Bam! So there's sulfur hexafluoride. And what you see is that sulfur has got more than an octet. The fluorines have got their octets, but the sulfur has got 12 electrons surrounding it, and it's jamming those extra ones into its d orbitals, which were empty until now. All right, PCl5. Phosphorus has 5. And 5 times 7 times 5 is 35. So we need to account for 40 electrons here. Phosphorus goes in the middle. And your chlorines go on the outside. And you put your dots. And what we have is basically 2, 4, 6, 8, 5 times, and that's going to give you 40. And phosphorus, again, has got more than an octet here because this is not obeying the octet rule kind of dude here. And then ICl4 minus, this is an ion, and the center dude is iodine, and the outside dudes are chlorine. So draw this. And in order to figure out the number of valence electrons, we've got 7 for iodine and 7 for each chlorine, so that's 7 times 5, so 35. But then this minus is an extra one, so there's 35 from the atoms, and then you've got an extra electron, so you have 36 total. So boom, 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 at least, and then all your dots. Pew, 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 pew. And that's going to be, again, 8 times 4 is 32. So where are the other ones? So 32 and 34 and 36. So iodine is joined to 6 electron domains here. And again, since this is an ion, you got to put brackets around it in order to make it perfect. We want to be perfect. Bam. All right, sorry about that, folks. That was my software being sort of weird. All right, so now we've got nitrogen monoxide. And nitrogen has got 5, oxygen has got 6, so that's going to be nitrogen, oxygen, at least 1 bond, at least 2 bonds, because oxygen likes 2, nitrogen likes 3, so we're going to have 2. And the thing that you need to notice is that this is 11 electrons, which is odd, and that's odd. So oxygen is going to have 2, 4, 6, 8, but nitrogen is going to have 2, 4, 6, 7. So that we have a total of 2, 4, 6, 8, 10, 11 electrons. So nitrogen has this lonely little electron here, which makes this a pretty reactive species. This one is odd, and so I would recommend memorizing it. The next two are actually related to formal charge and resonance structures, so we will get to them later. So let's switch back to our notes. All right. Resonance structures. Let's look at this example. We've got the nitrate ion, and you've got nitrogen with 3 oxygens, and the structure ends up being, in order to give nitrogen an octet, 2 of the oxygens have a single bond and 1 of the oxygens has a double bond. Well, it really could be this oxygen, but it could be this oxygen that has the double bond, and it could be this oxygen that has the double bond. And what ends up happening is, if a double bond could be in multiple spots, what ends up actually happening is that the real structure is an average of all the options. So you end up with actually the bonds being kind of 1 1/3 bonds in this case, instead of a single bond or a double bond, the electrons get shared kind of all over the place. This is called resonance, and these extra structure options that you kind of have result in them being more stable, and you have got these electrons that are called delocalized. They can move around between these several options here. So this nitrate ion has got resonance structure with a bond that is shorter than a single bond but longer than a double bond, and with a strength intermediate between the singles and the doubles. And you are going to need to be able to recognize when you have the opportunity for a resonance structure, and that's basically if you could have a double bond in several different places because you've got several different of the same option. So there you go. That's resonance. Whee! And then formal charge. Sometimes what you end up with is several structures that obey the octet rule for a single molecule, and you're not really sure which one is the correct one. And the answer is the correct one is the least unnaturally chargy structure. And so by that, you have got to know about formal charge. Formal charge is basically determining how many valence electrons each atom owns, basically, and has near himself, and that's going to be all of his lone pairs and half of the shared electrons. And so that's the formal charge of the atom, and what you end up looking at is that similar to their normal valence electrons? And if it is similar, then you're good, and if it's not similar, then it's not as good of a structure. So you compare them by subtracting. So let's look at this phosphorus molecule here. So what you end up doing for him is you've got phosphorus with an oxygen and a chlorine and a chlorine and a chlorine. And phosphorus has 5 valence electrons, oxygen has 6, and chlorine has got 3 times 7, so 21. So what you end up with is 21 plus 5 is 26, plus 6 is 32. So you have 32 valence electrons total. And so you kind of go, all right, phosphorus, oxygen, chlorine, da, da, da. So you can say, all right, we could have a double bond on this oxygen here. That would be 2, 4, 6, 8, 10. And that would leave us like this, dot, 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 dot. So that's a possibility. Another possibility that you might want to consider is a single bond with the oxygen and a double bond with one of the chlorines. Now I know this is unusual, but it's possible because we know that chlorine can have more than an octet. So chlorine going to a double bond with chlorine. And what you end up doing is going, okay, so for phosphorus, normally phosphorus has got 5 valence electrons. Right now, phosphorus owns half of this bond, half of this bond, half of this bond, and half of this bond. So he owns 1, 2, 3, 4, 5. So the formal charge on phosphorus is 0. 0. For the oxygen normally has 6. And in this, oxygen owns all of its lone pairs, so 1, 2, 3, 4, and half of the bonded ones, 5, 6. So on oxygen, the charge is 0. The formal charge. It's not a real charge. It's sort of a pretend charge. And then for the chlorines, you have, normally you've got 7. And what chlorine has is all of its lone pairs, so 1, 2, 3, 4, 5, 6, and half of its bonds, so 7. So what we end up with is basically a score of 0, 0, 0. All right, let's compare that to this guy. Phosphorus, again, normally has 5. Subtract off what he's got in the bonding, 1, 2, 3, 4, 5. So phosphorus, again, has a score of 0. The oxygen normally has 6. And in this case has got 1, 2, 3, 4, 5, 6, and 7. So oxygen is showing that he's got an extra electron than normally on his valence electron. So that's -1 score for oxygen. For the single bonded chlorines, we've got 7 minus 7 again, so we've got 0, and there's 2 of those, so 0, 0. And then this double bonded chlorine normally has 7, but in fact is showing 1, 2, 3, 4, 5, 6. So that's going to be a 1. So we have a score here of 0, 1. I guess this is 0, 0, 0, 0, 0, 0, 1. Stop it. 0, 1. No, 0, -1, 0, 0, 1. And so you're looking at these and going, well, these are both possible structures. They both could happen. But what we can see from the formal charge is that zeros usually win. So it's least unnaturally charged. So 0, 0, 0, 0, 0 is a score that is better than 0, -1, 0, 0, 1, because zeros are superior. If you can't find a score that's all zeros, the negatives, like this, it's better to put those on electronegative atoms because they suck electrons toward themselves. So we will see an example of that in a little bit. All right, but that's formal charge and resonance structures. And now I'm going to go do the rest of question 3 and question 4. So you go ahead and do those and meet me on the black screen. All right, so here we have nitrogen dioxide with nitrogen. Oop, we're on eraser apparently. With nitrogen in the middle and oxygens around the outside. And I have a little bit of trouble with this one because I'm not really sure where to put single versus double bonds, so we're going to try all of our options. And so let's do a bunch of singles. So we've got nitrogen single bonded to oxygen, single bonded to oxygen, and then you're going to have 2, 4, 6, 8, 10, 12, 14, 16, and then 17, which, by the way, 5 and 12 is 17. And we see here that we have the problem that nitrogen has only got 2, 4, 5 valence electrons. So this is not going to work out. So single bonds, boo. With 2 double bonds on either side of nitrogen, you make both of the oxygens happy with the number of bonds they have. But you can see again 2, 4, 6, 8 for oxygen, 2, 4, 6, 8 for oxygen. That's 16. Where does the last electron go? You can't have an expanded octet for nitrogen and oxygen because they're not on the third row. So double bonds, both sides doesn't work. So we're stuck with some kind of 1 double and 1 single situation here. So with that, then we get into a question of formal charge, as you will see, because what we can do is we can go, okay, 2, 4, 6, 8, 10, 12, 14, and then you kind of go, well, we've got 3 more. We can do 2 on nitrogen to make his octet complete, 16. Then the 17th one, I guess, would go on the oxygen. So we've got nitrogen with an octet, oxygen with an octet, and oxygen with a septet? Not sure. All right, so the next one we can do, same deal. What we can do is go, okay, 1, 2, 3, 4, 5, 6. We can put that single electron on nitrogen and make the oxygen happy. 2, 4, 6, 8, 10, 12, 14, 16, 17. Or we can make these guys both happy. 2, 4, 6, 8, 10, 12, 14, 16, 17. So what we have is a single electron, a radical here. That's what they're called when you've got a little single lonely dude. And these all work just as well as each other. You can't really get an octet, but you can get close. So this is a situation in which you have to calculate your formal charge. So for the leftmost oxygen, normally you've got 6 valence electrons, and in this situation you've got 7. 6 minus 7 is -1. And for nitrogen you've normally got 5, and in this situation you've got 1, 2, 3, 4, 5, so that's 5 minus 5, that's not bad. 0, and then oxygen you normally got 6, but instead we have 1, 2, 3, 4, 5. So this gets a score of negative 1, 0, 1 for that guy. All right, for this guy, we've got 6 minus 7 is negative 1, and we've got 1, 2, 3, 4, so that's 5 minus 4 is 1. And then we've got a situation which is 1, 2, 3, 4, 5, 6, so 6 minus 6 is 0, so we've got negative 1, 1, and 0. And we've got this one, which goes 1, 2, 3, 4, 5, 6, so 6 minus 6 is 0. 1, 2, 3, 4, 5. 5 minus 5 is 0. And 1, 2, 3, 4, 5, 6. Hey, 6 minus 6 is 0. So of these 3 options, none of which are perfect because we can't get an octet on everybody, the last one is superior because its formal charge score is 0, 0, 0. So that's the Lewis structure. These lose. And these definitely lose because nobody's happy. All right. Now, N2O4 comes from the joining of 2 of these guys, and what you end up with is N's in the middle, and with at least 1 bond each to their oxygens. And that's 10 and 6 times 4 is 24, so 34 total valence electrons that we have to account for. And let's see, we've got 2, 4, 6, 8. And it's interesting because the nitrogens have got 3 bonds, and the oxygens have got 1 bond. Oxygens prefer to have 2, so we can try that one and this one, let's say. If we try all 4, that doesn't work because then the nitrogens are 2, 4, 6, 8, 10 valence electrons, so let's erase a couple of those. So now the nitrogens have got 2, 4, 6, 8, 2, 4, 6, 8, and that makes a nice octet, so we can give this one a shot. This oxygen would get 2, 4 more, 2, 4, 6, 2, 4, 6, 2, 4. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34. So that's great. So that works. Not the double bonds all over the place doesn't work, and single bonds doesn't work all over the place. So 2 double bonds and 2 single bonds. But what we can see here is that we have a couple of options in terms of the locations of the double bonds. We could have 2 ups, we could have 2 downs, or a crosses here. And what you have to remember is that the double bonds repel maximally compared to the single bonds, so they are more repulsive. They're kind of a stronger electron domain. So in fact, this is not as good as doing it this way, in which you have the double bonds kind of squeezing apart from each other so that they are not nearby. So that's the Lewis structure for N2O4. All right, and now question 4. All right, here we have the sulfate ion, and what we can do with that is we put sulfur in the middle and oxygens around the outside, and at least 1 double bond between them. Oh, and let's calculate our valence electrons. That's 6 for sulfur and 24, and then 2 more, so 32. So 32 valence electrons. And let's see, it's hard to decide whether we're going to do single or double bonds, so let's do all of them and see which one works well with the formal charge deal. So in this case, we can do 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and that's going to be in brackets with a 2 minus on the outside. And that's 8 4 times, so that's 32 electrons. All right, we could also have, and what we have is sulfur with an octet here, but one thing that we know about sulfur is that sulfur can have 10 or 12, so we've got to check those as well. So 1, 2, 3, 4. I suppose we could have 1 double bond. That's 2, 4, 6, 8, and then so 32 again. So we've got a 1 double bond and 3 single bonds. And we can also have an option with a pair of double bonds. With sulfur having 2, 4, 6, 8, 10, 12 instead of an octet, and 10 instead of an octet. So let's calculate our formal charges. We've got sulfur, which normally has 6 and here has 4, so that's 6 minus 4 is 2. And we have our oxygens, which are normally 6, but instead here they have 7, so 6 minus 7 is -1, -1, and -1. So that's our score for this first guy. And the score for this one is the sulfur again normally has 6. 1, 2, 3, 4, 5. So in this case we've got 6 minus 5. So 1. The double bonded oxygen normally has 6 and it's got 1, 2, 3, 4, 5, 6. So that's going to be 0. But the single bonded oxygens again are 7, so that's -1, -1. -1. And we need another -1 over here, by the way, because there's more. Alright, so that's the score for the second one. And the third one, we've got sulfur 1, 2, 3, 4, 5, 6, so that's a 0. And 1, 2, 3, 4, 5, 6, that's a 0 and a 0 for your double bonded oxygens. And your single bonded oxygens, you've got the -1s again. So I know what you're thinking. You're thinking, well, can't sulfur have more so that the oxygens are happier? It can't. Sulfur is not observed to go above 12. So here we've got 12 electrons around sulfur. He's not going to get any bigger with his expanded octet thing. So our best score is 0, 0, 0, -1, -1. So here is our best structure. Bam. All right, next, same deal, but with the perchlorate ion, ClO4 minus, which has got 7, and 6 times 4 is 24, and 1, which is again 32, and you end up doing the same deal. So chlorine in the middle, and oxygens around the outside, and all single bonds. And it's an ion, so minus, and that's 8, so 32 each, 4 times. And the score for this is chlorine, which normally has 7, has 4, so that's a 3, and then all these oxygens have got scores of -1. All right, next we'll try it with 1 double bond. And our score is slightly better for chlorine now. We've got 5, so that's 2. And the double one is a nice 0, and then we've got 3 -1s again for those single bonded oxygens. And then chlorine can have maybe 2 double bonds, let's say. And we end up with a score of 7 minus 1, 2, 3, 4, 5, 6. So 1, and then a couple of 0s for double bonded oxygens, and a couple of -1s for our single bonded oxygens. And we can't keep going because, again, chlorine is only observed to get 12 in its expanded octet. So our best score is this one, with the 2 double bonds. And the same deal goes for xenon hexaoxide. Nope, tetroxide, not hexa. Xenon tetroxide. You end up with xenon, Try single bonds. And hey, there's no brackets on these because this is not an ion. So xenon normally has 8, and here it has 4, so we have a score of 4, -1, -1, -1, -1. And with a single double bond, with only one double bond, you have a score of 3, 0, -1, -1, -1, and with 2 double bonds, you have a score of 2, 0, 0 for your double bonded oxygens, and -1, -1 for your single bonded oxygens. And so that is again the best score. And what you may have noticed is that the best score for all 3 of these central atoms with 32 valence electrons surrounded by oxygens have got 2 double bonds. This score, and this score are all the best options for the sulfate ion, the perchlorate ion, and xenon tetraoxide, and that is actually a pattern that I've noticed, so keep that in mind.